Okay, so in the last lesson we looked at calculating the area between a given function and either the x-axis or the y-axis. What we're going to look at in this lesson is calculating the area between two curves. Basically, you're given two functions and you want to find the area between these two functions over some interval. So we'll start here by just sort of visualizing what this situation would look like, and we'll go back to some of the stuff that we did when we were just learning integration to sort of justify the approach that we're going to take. So let's say we have some function here. We'll call this f2 at x, and then we've got some other function that might go like this. We'll call this f at 1 at x. So we're given these two functions, and what we're asked to do in the question is find the area between f1 at x and f2 at x, and of course we'll always be given some limits here from a to b. Okay. So let's we'll pick a value for a here, and then we'll pick a value for b over here. So back when we were learning about integration, we said one way of sort of estimating the area under a curve was to take the area and divide it into a bunch of rectangles. So we can imagine doing that again. Taking this thing, subdividing it into a whole bunch of little rectangles. And let's say the width of each one of these rectangles is, again, delta x. If we wanted to calculate the area of one of these things, so we've got n rectangles of width delta x, okay, what is going to be the height of one of these rectangles? Well, it's going to be given by the particular value of function 1 and function 2, basically the difference between them. So the height of each one, in this case, it's going to be the value of f2, okay, basically the top of the rectangle, minus the value of f1, essentially the bottom. Take the top, subtract the bottom. Okay. Now, if we wanted to, so our area would be, well, the area of one individual rectangle would be f at 2 at x minus f1 at x. So our height times our width, okay, gives us the area of one rectangle. We want to take the sum. Basically, we want to add up the areas of all of our individual rectangles. So I goes from 1 to n. So we're adding up all of the individual rectangles. And if we want to make this a really, really good approximation to the actual area, we want to use as many rectangles as possible. And if we want to make this a perfect estimation, we are going to take the limit as n goes to infinity. Okay, just like we did when we were just doing integrals. Okay, so we know what this thing is. This thing, if we take the limit as n goes to infinity, we have a special name for this. This was our definite integral. So the area is going to be our integral from a to b of f2 at x minus f1 at x. Okay, and we'll put this in sort of square brackets here because we want to do that difference first. And rather than having delta x over here, we're going to have dx because we're integrating over dx. So this sort of expression here is how we're going to calculate the area between our two curves. Okay. So another way of thinking about this is, let's see, if f2 at x and f1 at x are both positive, okay, on our region, and f2 is greater than or equal to f1, right? So let's just, both of these things, let's see, f2 is greater than f1, so f2 again is up here at the top, f1 is down here at the bottom. I've drawn these so that they're both greater than 0, so they're both positive on our interval a to b. How else can we think about this integral that we're trying to do here? Integral from a to b, f at 2 of x minus f1 at x dx. Well, we also learned that you can take these integrals where you've got a difference of two functions, and you can split it up into two separate integrals. So we can split this into the integral from a to b of f at 2 at x minus the integral from a to b, oh, I forgot my dx in there, f2 at x dx minus the integral from a to b of f1 at x dx. So let's think about what these two separate integrals represent. This first one, the integral from a to b of f at 2 d at x, what does that represent in terms of our graph here? What do you think, Daphne? Yeah. So between the x-axis, so it's the, not the distance, but the area under f2 at x. Okay, so it would be sort of this red area all the way through here. Similarly, if we look at our second integral, the integral of f1 at x from a to b, it represents the area under f1 at x. So basically it represents this blue area. If we subtract these two areas, basically we take the red area, we subtract the blue area, what we get is this green area, which is our area between our two curves. Okay? So the area that we want, I don't know how I can write that. I'll just draw like a nice little picture here. There's our green little area, blah, 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 which is the area that we actually want, the area between our two curves. So that's the approach that we are going to take, okay, in answering these kinds of questions. So let's take a look at an example here. Find the area between y equals x squared plus 1 and y equals x from x equals 1 to x equals 3. So we're given our two functions, and we're given our limits of integration from 1 to 3. So what would this one look like? If I do a quick sketch over here, our first one is a parabola. Our second one is a linear function going kind of like this. So the region we're finding the area of looks something like this. Okay, going from 1 to 3. So in this example, we have one function, y equals x squared plus 1, is always greater than our other function, okay, y equals x. So this is, I'll say x squared plus 1 is up here, and this down here is y equals x. So again, we're just going to do this integral. Integral from 1 to 3 of our upper function, x squared plus 1, minus our lower function, which is just x. Put this in some square brackets here, and integrate over dx. Now to make this integral a little easier, I mean, we'll just rewrite it a little bit here. We can combine these terms together. X squared minus x plus 1 dx. Okay, so this integral is, I mean, it's not a hard integral. We've been doing a bunch of these like this for the past few weeks. We just need to find our antiderivative here, which is going to be 1/3 x cubed minus 1/2 x squared plus x. Evaluate this from 1 to 3, and well, we end up with something. If we punch this into our calculator, we would get something like 10.6 minus 4. So our area is, I should say, approximately equal to 6.6. Okay. So the next example we have here, find the area of the region between y equals x squared plus 3 and y equals x plus 1 from 2 to 4. Yeah. That one. All right, let's do that one as well here. All right. So again, I'll do a quick sketch here. We've got x squared plus 3. It's our parabola. Y equals x plus 1. So it's going to, the y-intercept of our parabola is going to be up at 3. And our function is going to go kind of like that. Okay. And then we're going from 2 to 4 like this. So we want this little region in here. Okay. And I'm doing these sketches basically so I can see which function is my upper function and which one is my lower function, because we always want to do the upper one minus the lower one. That's how we decide which one is F2 and which one is F1 in this case. So if you were doing this sort of on the exam, that's where your graphing calculator comes in handy. If you're not sure which one is the upper, which one is the lower, you can quickly graph both of them just to make sure that you're doing this in the correct order. Your other option would be to evaluate the two functions sort of at the endpoints and see which one is greater. So again, in this case, our area is just going to be the integral from 2 to 4 of our upper function. So I got big square brackets there. Let's put our upper function in round brackets, x squared plus 3. From that, we want to subtract our lower function, x plus 1, and integrate that whole thing over dx. And just like in the previous one, we can do a bit of simplification here. We can rewrite this as x squared minus x, let's see, plus 3 minus 1 is plus 2 dx, which again is a fairly straightforward integral. We'll have 1/3 x cubed minus 1/2 x squared plus 2x evaluated from 4 to 2. And again, you probably just, unless it asked you for an exact answer, you would probably just plug this into your calculator. And again, you get 16.6 repeated here. Okay. Right. So example 1 and example 2 are very straightforward. They give you the limits of integration. They give you the two functions. The functions are well behaved in that one of them is always your upper function, one of them is always your lower function. A trickier kind of question is what we have in example 3 here. Find the area between the graphs of y equals x squared and y equals 2x. Okay, so they give us the two functions, but they don't give us any limits of integration. And the reason is, well, if we were to sketch what is going on here, we have y equals x squared, which looks like this. And y equals 2x will go kind of like this. So the area that they want us to find is the area bounded by these two curves, essentially this little area in here. And they don't give us the limits of integration because the limits of integration are defined by the intersections between these two curves. Okay? So the first thing to do in a question like this is figure out where do our two curves intersect. Now this one is a pretty simple one to solve. So if we want to find where these two things intersect, we can just set these two functions equal to each other. They intersect, I should say they intersect where x squared is equal to 2x. We want to solve this thing for x. And we should get two solutions, one at one limit and one for the other limit. So I think the easiest way to solve this is bring everything over to one side. So 0 equals, let's do it the other way. X squared minus 2x equals 0. We can factor this. X times x minus 2 equals 0. And that gives us our two solutions. X equals 0 and x equals 2, which we can kind of see from the graph. Clearly, we have one of our intersections at x equals 0, and the other one is over here at 2. Okay. So now we want to do our integral here. So what is our integral going to be? We want to do the integral from 0 to 2. And what are we integrating? Well, we're integrating our upper function minus our lower function. So in the region that we're interested in, our upper function is y equals 2x. Okay, so it is our upper function in this little area right in there. So that's the one that we want to have first, 2x. And from that, we want to subtract our other function, x squared dx. Now, if you get those backwards, you do x squared minus 2x, you'll get the same numerical answer. It'll just have the opposite sign. You'll get a negative area. Okay? So in some cases, you can actually set it up wrong, realize at the end that you've set it up wrong, and just correct your answer by changing the negative sign to a positive sign. But then you would just do this integral. What do we get here? X squared minus 1/3 x cubed. Sorry, evaluated from 2 to 0. And you can work all that out. You get 4/3.